Hey everyone. So welcome to this second part of the gradient descent lecture with a focus on helping you getting gradient descent up and running or understanding gradient descent for deep learning and machine learning applications. So in this lecture, what we'll do, or this part of the lecture, what we'll do is we will set up now a more general version of gradient descent. In the first part, you just saw a simple one-dimensional example. We'll kind of set up how a more general version works. And then we'll set up a simple nonlinear regression problem that then we will code up in the third part of this lecture. So at the end of the third part, you would have gone from simple example and understanding the basic idea to actually implementing a nonlinear regression problem with gradient descent and seeing how it works, right? Okay, perfect. So in the previous lecture, like I mentioned, you got a basic understanding of the intuition of gradient descent, right? We looked at the idea of a climber trying to get off a hill or get down from a hill, and he has limited visibility. So what he has to do is look at the direction of the gradient, right, of the terrain around him, meaning he has to look around and see which way, the slope of the ground around him is the steepest. And assuming he has the skills, he then uses that to find his way down, right? Um, and then what we did once we understood the basic idea, we then went in and applied gradient descent to find the minimum of a simple quadratic function in one variable w, right? So this is a simple function, and you see the function here. And what we did is we said, well, okay, we know, like the name suggests, the gradient descent. In gradient descent, the gradient gives you the direction of the maximum increase of a function, right? And so, well, we want to find the minimum. We're going to go in the direction of opposite to that, right? Because we want to find the lowest point. So what do? You take the function, you find the derivative or the gradient in this case. And then we take a learning rate which scales this derivative and use this simple algorithm. So you start at an initial point, which is wi. In this case, I will be the first point, right? So you can call it w0, let's say. And then what you do is find the derivative or the gradient at that point, multiply by this learning rate, and then subtract that from the w. And that would give you a step, right, in the direction, because it's opposite to the direction of the gradient, it would give you a step in the direction of the minimum of that function. And you'd keep doing that. So that would become wi plus 1. Then you'd update I and you'd get at the next iteration, you'd do the same thing. Now at that point, you'd compute the gradient and so on till you got to the lowest point here or the minimum, right? And we found that the algorithm does quite easily find the minimum for this simple one-dimensional quadratic function. Okay. So now let's look at a more general example, right? That was a simple one-dimensional example. But what if you have multiple variables, right? You're solving a deep learning problem, you have a number of neurons, so their weights and biases come in. Not as simple as W1, W. You have, say, W1 to Wn, right? Lots of weights, and say the biases are included in that. Could also be a machine learning problem with a lot of weights and biases. And so what do you do? Well, let's say you take the first variable, you apply the same algorithm, right? You say you have an initial guess, and then you say, okay, I'm going to take the value, I'm going to find the derivative with respect to W1, scale by a learning rate, and we're going to keep the learning rate the same for all the variables for now. And then you subtract that. So it's just this, but now you're doing it for the first variable. You do the exact same thing for the second variable and the third variable and so on. So what you end up with is this very simple, extension to this algorithm, where what you have done now is for each variable, you have just done the exact same thing. You've taken a value or taken an initial guess and then computing the derivative and stepping in the direction opposite to the derivative, right? So descending against the gradient, basically. Now, is there a better way to represent this? There is, right? So, well, you can say all these W's can be put together in this simple column matrix, right? You can think of it, you can either just think of it as all your variables put together in a matrix, or you can think of it as a problem, right? Modeled by this vector, right? With these many dimensions, right? And if you're not familiar with vectors, a short course on that is coming on soon. So I'll add a link to that, right? So that'll kind of help clear your doubts. But basically, you can think of all the W's being stacked together. That's an interesting way to think about it. and assume now W represents this vector, right, with each of these um, Wi, W1, W2, W3 stacked. And then you say now, well, the derivative of f with respect to each of these now, right, is also stacked similarly. And what that is the gradient vector. So it's the gradient of that function with respect to W, right? And it's basically just the differentiating W with respect to W1, and then the partial of f with respect to W1, the partial of f with respect to W2, and so on stacked together. So this now becomes the gradient of that function in a simple one-dimensional case. Well, all of the others go, which is W1, and the gradient was just the derivative with respect to W1. In a multi-dimensional function or in a problem with multiple parameters, the gradient now is basically just the derivative, the partial, but with respect to each of those variables, right? And it would give you the yeah. So let's look at how the algorithm would shape up. Well, it's the same, only now you can replace W1 here with W. And in the one-dimensional case, in the previous example, or in the previous video, W was a scalar value, right? It was just at one weight. In this case, now W represents this vector, and that W is equal to Wi, meaning this vector, the state at I, which is the ith iteration, minus learning rate, which we're going to keep constant. It's not going to change for the parameter for different W's for now, times the gradient vector, right? And so now you've got a simple vectorized version of this, and this is gradient descent for a multi-dimensional problem, right? So it's actually still very simple. Let's take a simple two-dimensional example, right? So let's say you have a space W1 and W2, right? So it's a two-variable problem, quite simple. And so you have your W now, which is now W1, W2, and you have your del F, which is dou F dou W1 and dou F dou W2, right? So now if you look at this here, the X and the Y, I've just written X and Y here simply because, well, I guess the W2 is on top of the Y, because that's kind of typically what you do when you draw a plot, right? If you're familiar with that, in two-dimensional, you have X and Y. And then the color here is basically a contour plot indicating the value of that function, right? So it's a nice function where given a W1 and a W2, you can see the value, the color code indicates the value, right? And so what you do is, let's say at an initial point, you have, say, W1 is 4 and W2 is, say, -3, right? Looks around -3, right? So at that point, you've got this initial guess and you see what the function value is. It's somewhere in this range. And then what you do, well, you compute the gradient vector. Now it's not just one dimension. So it's not just W1 that it's changing, and it's W1, W2. So you can think of it as a direction. The gradient is going to be in the direction of increase, right? So it's going to, in this case, the colors, as they get lighter towards the yellow, it's increasing. As it goes towards the blue, it's decreasing. So the gradient would be in this direction. You're going to move opposite to that. So you take a step here, right? Opposite to the gradient. Obviously, the learning rate would determine the size of the step. And then you'd compute the gradient here, and again, it would point this way, so you'd go in the opposite direction. And you'd keep taking these steps till you got to the minimum, which in this case is around -8, right? And so, and as you get closer, like we saw in the one-dimensional case, we see here that the steps become smaller because the gradient's becoming smaller and smaller, right? And so you're getting closer, and the direction kind of slightly angles in, right? And you get to the optimum. Right? So it's a simple example in a two-dimensional space. We aren't going to code this up because we are going to code up a machine learning problem. Right? So let's. The idea here is you understand what I mean by a two-dimensional example or multi-dimensional example. It's now W1 and W2 both changing. So you can think of it also as coordinates in this example, X and Y, and the X and Y's are changing in this direction. And you could have a more complicated problem with multiple dimensions. It would be hard to visualize. But now it's effectively the same thing, right? Where W would be that point in that space, and del F would be the gradient indicating in which direction you'd need to move, right? In that space to increase the function, so you'd go opposite to that. Okay, so let's now write down the general gradient descent algorithm. And if by any way, if you're not familiar with vectors and you don't understand the vector analogy, don't worry about it. We'll put a course out in vector on vectors because you'll need it anyway as we learn more deep learning and new NLP and so on. So it would be a good idea when that comes out to be familiar with it. But also, if not, just think about it as just the parameters aligned in an interesting way in a matrix, and the gradients or the sensitivities, right? The partials with respect to each of the parameters aligned in our matrix. So what would you do in the algorithm? Well, you have an initial value for each of these parameters. And they might, depending on the problem, you might either initialize it to a random number, or if you know a good initial estimate, you'd use that. And you're on the 0th iteration. So ideally, you don't check converge. You don't need to. I mean, if you already converge, why would you do this? So you won't check convergence necessarily here, but I've just written it here. Assume not converged, right? Now what do? You go in and you compute the value of the function given this vector input and any other parameters you're passing in. So for example, in a data, machine learning problem, you would actually pass in the data point, right? Apart from the weights. So that's why parameters. And then you'd also get the gradient. Now I'm assuming this function gives you the gradient. And in the problem we'll set up, we will actually get the gradient for that function. But otherwise, you could have two function calls, right? One that gets you the function value, one that gets you the gradient. If by any chance you're using, an alpha I, a learning rate that is dynamic and depends on the iteration and things, which will be advanced algorithms, so you don't need to worry about it for now, then you would compute that. But that is for a gradient descent variant, right? So simple gradient descent, vanilla gradient descent, you wouldn't. And then what you do, the simple algorithm, now only the difference is W is this entire column matrix or vector, and F is this del F, the gradient is this column vector as well. And you'd say you take Wi at that point, subtract alpha I times the gradient, right? Which is basically you'd just be subtracting Wi minus alpha this term, W2 minus alpha this term, and so on, right? And you'd get another W, which is the next, which is basically the value for the next iteration, right? So it's the next step. This is the next step, and you get the next value. What would you do? Well, you'll say, okay, I'm going to update I, right? I've done this is 0th iteration. Okay, now I becomes 1. Go back. Are you converged? Probably not. So keep doing this till you're converged. What do we mean by converged? Well, as we saw in the first example, for example, in the previous lecture, that is, that at some point the function, right, which in a machine learning problem, say your loss is kind of flattened out, it's not decreasing anymore, or it's below a tolerance. You say you want an error of, acceptable error of say 5%, and you are at 4.8, and so you feel, while we are converged, we don't need to do this anymore. You say I'm done, and the W there, now we'll call it W star, is your actual solution, right, of the gradient descent. So hopefully this is really clear, right? And you've understood it's a very simple algorithm. And the one-dimensional case you can see is exactly this, right? And so it's multiple dimensions. You're just doing exactly the same thing, but now for each of the dimensions or each of the variables, right? Okay. So now that we've understood that, let's set up the gradient descent problem for machine learning and deep learning. Okay. So this is a data set. X and Y indicate the variables, right? So you have W1 and W2. So X and Y axis here. And then this axis is the actual value of the function, right? That's how it's shown. So this indicates the value, and these two indicate the coordinates. So what we want to do is take this data, right? And when we code it up, we'll also then have a variant of this. And we want to see if we can fit this function to this data. So now what happens is, in the previous example, we were trying to find the minimum, right? So in that case, you would already know W1 and W2. What you're trying to do is find the X1 and X2 that gets you to the minimum. This is a very different problem, right? In this case, you have a set of X1s and X2s. You know the X1 and X2 here for each thing. What you're trying to solve for is the W1 and W2, which is why I've used W and W. In that case, I just used W as the variable, and you found the minimum. But in this case, actually X1 and X2 are the data points, and W is the actual value that scales it. So kind of like a weighting parameter. And you want to find these two such that this kind of function models this data as well as possible. So it's an example of what the data looks like. x1 is -1 and x2 is -1, you get, the y, which is the value, is 2.407. You have that for another data point and for another data point, and we have quite a few data points there. And so first thing we need to do to run gradient descent is to understand the function we're running the algorithm on, right? The f that we were seeing there, right? And so that's called the objective function, right? So what's the objective function? Well, the objective function here is, think about it, you want this to model this data well. So it's the error, right, in this prediction, right? You have the actual value given those two data points, given the two coordinates. You substitute those two coordinates into this function, and you assume or start with an initial guess of W1 and W2. You'll get an estimate of what the function gives you, right? Which is your error. And I say W, I mean the vector W, so it includes W1 and W2. So you get the value that this f predicts given x1 and x2 for a particular W1 and W2. You compare that with what you get here, and the difference is the error. What you want to say is the error needs to be minimized, right? If possible, the error is 0, in which case the function models the data perfectly. So I'm going to define error as the difference between y, which is the actual value, or you can call it the label, and the actual and the value predicted by the function for a given W1 and W2, right? And what I'm going to do is I'm going to square this. Why am I squaring this? Well, you want the actual error not for one data point. Right? If it's one data point, you can do y minus f, and you can say I want to find a way to minimize that. Even there is a problem. If you minimize that directly, it will try and make it very negative. So you can say absolute value, right? But we want to sum across a number of different data points. So absolute value is okay. What we are going to do is we're going to say, well, I'm going to use the square, right? So what that does is it ensures that you sum across, right? And so what your function now will become is this error now, right? And j indicates the index of the data point. So this would be j is 1, this would be j is 2, this is j is 3. So for each data point, the error is the actual value minus the predicted value square. I'm going to sum across j. So what this notation indicates is that you're just adding each of these ej's for all the j's. So for all the data points, you're just adding. That's what this indicates. And then I'm going to divide that by the number of data points. So n indicates the number of data points. So what you will do is you'll say, okay, for data point 1, I'm going to take y1 minus f1. I'm going to square it. Then I'm going to say plus y2 minus f2 square plus, and so on. I'm going to do that for all my data points. Let's say there are 200. So I'll do it for all 200, and then I'll divide that by 200. So it kind of gives you an average square error, which is why it's called the mean square error. It's the square of the error, and it's the average of that, right? That's a really good indicator, or a really good error estimation model that's used in machine learning problems, and also in deep learning problems when you're trying to do regression with a deep learning. So we've got our objective function. We want to minimize this function where you want to find the error at each data point for a given W1 and W2. You want to find the error in the prediction. You want to square it and sum it across all your data points and divide by n. So it's your average error for the data set given a W1 and W2. And you want to optimize or use gradient descent to find the best possible W1 and W2 that minimizes this. And so we're going to call this entire objective a loss function. So it's the sum of the individual errors. Great. So we've got our objective. What do we need next? We're using a gradient descent algorithm, but you need the gradient of the loss function with respect to, in this case, the two variables W1 and W2. Great. So let's go find that. So let's start with just W1, right? And once you understand W1, then even if you have it's a much more complicated problem and you have, say, 20 Ws, you would actually be able to solve this, right? But luckily for us, it's only got 2 Ws. So I want the derivative of the loss with respect to W1. That will be equal to 1 by n, which is the average. Now, technically, 1 by n should be here as well, but n has got no dependence on W, so I've taken it out straight away. So it's 1 by n times dou by dou W1 of the sum of the errors, right? Now, what does sum rule of differentiation tell us? Well, if you're taking a derivative of a sum of values, then you can also sum up the derivatives, right? Which is represented by this. What you can do is say, well, I wanted dou by dou W1, 1 by n is outside. So that's already there. Right? Suppose you want dou by dou W1 of E1 plus E2 plus E3 plus E4 and so on. You can say, well, actually, that's equal to dou E1 by dou W1 plus dou E2 by dou W2 or dou E2 by dou W1 and so on, right? You get this term. Why do we do this? Because now we can compute this error for a data point with respect, right? We can then get the derivative of that one error term. We can do the same thing for the second and the third and so on. So they're independent now. The computation becomes independent. You can just do this for each data point and you can add them up and divide by the number of data points. And so as we can see, you can do exactly the same thing for W2. You can get the derivative of the error for each data point with respect to W2 and then average it out. So how do we now get the derivative of the error for each data point? Interesting. Well, this is part of the deep learning series, or if also kind of part of machine learning problems. Favorite differentiation technique comes in chain rule. So you don't need to use chain rule. You could just substitute this here, but I'm using chain rule here. I'm saying, okay, I want the derivative of the error term with respect to W1, which shows up here. The simple way to do it is to say, I'm going to take the derivative of EJ, the error term of at the jth data point with respect to the function at the jth data point, right? Because this derivative term is going to be very simple. And then I'm going to take the derivative of the function at the jth data point with respect to W1. And you can do exactly the same thing for W2. I can take the derivative of the error term at the jth data point with respect to f, or the function at the jth data point. And this is analytically, right? The advantage of this is we're doing this analytically to get the value so that we can code it up. So it's just an analytic exercise, right? So bear with me on this. And then you can take the derivative of the function with respect to W2, and then you multiply that. Great. So let's do that for W1. We want the derivative of f with respect to W1. Now I'm taking out the j here because actually, no matter what the j, you're going to get the same answer, right? Analytically. You're not going to get the same answer as in the value. You're going to get the same derivative term, and then you would substitute. So dou f by dou W1 is dou by dou W1 of this term. Sum rule, you break it down into three different terms. The dou by dou W1 of this term plus dou by dou W1 of this term minus dou by dou W1 of this term. Now, if you remember your differentiation, W2 and X2 have no dependence on W1. This term goes to 0. This is a constant, right? 1 is a constant. No dependence on W1, that goes to 0. You're left with just this term, right? And if you don't remember your differentiation, you can check out, I'll add it in the link. You can check out our lecture on intro to a review of differentiation, right? And it is also a review on chain rule. So you can check that out if you don't remember, how that works. And that'll kind of get you up to speed very quickly. Okay, so you've got the derivative of this. Now what do you know? We know, well, x1 has no dependence on w1, right? x1 is a data point, w1 is your weight. There's no dependence, right? So you can take this x1 square outside this derivative. You're left with x1 square times dou by dou w1 of dou w1. So it's the derivative of w1, the partial derivative of w1 with respect to w1, which is 1, right? The derivative of something with respect to itself. The idea of a derivative is you're changing something. You're changing w1. How much does the numerator change by? Well, if you change w1 by 1 unit, the numerator here, if x1 is outside, w1 changes by 1 unit. The output, the answer of that is x1 square, where x1, for this particular example, right, is the x is the jth data point, xj. X1 is just the first variable, right? And x2 is the second variable. So it's just x1 square. Okay. Similarly, do the exact same exercise. So I'd actually encourage you to take a pen and paper and just do this for W2. It'll be good practice. You would get dou f by dou W2. And in this case, it's this term, right? So this, no dependence on W2, no dependence on W2. It would be this term. Same principle. You'd end up with x2 square, right? So we've got the derivative of the function with respect to W1 and W2. It would be x1 square and x2 square. And so at the jth data point, it would be xj1 square. That's why I haven't put the j here. It's just too much notation. It'd just be the first variable at the j data point, and you'd square that, and the derivative with respect to W2 would be the second value at j, and you'd square. So the first part of the one half of chain rule is done. We need the other half of chain rule, right, which is common, which is now the derivative of the error term with respect to the function, right? Now this differentiation again is quite simple. The derivative of the error with respect to f, right? Derivative of, yeah, with error term with respect to f. So let's write it out. So what you do, well, you take this, and the derivative of this would now be, if you remember your differentiation, would be 2 times this term times the derivative of that term with respect to fj. And an exercise for you, how did we get this, right? So the hint is, it's using chain rule again, right? If you say let z is equal to this term, right, yj minus fj, and you say I want the derivative of, derivative, you can use chain rule to say I want the derivative of this with respect to z, because it would be dou z square. So you can say derivative of that term with respect to z times the derivative of z, which is yj minus fj with respect to fj. That's the basic idea, right? Don't get confused, but I would again encourage you to try it out. It's good to practice your differentiation if you're going to get into deep learning and machine learning. So it's basically 2 times this term times the derivative of this term again, but now without the square with respect to fj. If you look at this term, yj is not dependent on fj. Fj is dependent, it's 1, but now there's a minus sign, so it's minus 1. So you'll end up with minus 2 times yj minus fj, which is not the error term we use in terms of E, it's just the difference between the predicted value and the actual label. Right? Okay, so we've got this. We've got these two. Let's use chain rule. We'll get the derivative of the error term at the j data point with respect to W1. Take this term, minus 2 times the yj minus fj, where yj is the label or the actual value, fj is the predicted value at the j data point. Multiply that by x1 square, where x1 again is at the jth data point, right? So remember that everything is j with respect to j. I've just not added the j here because the notation is too messy. And similarly, dou ej by dou w2, exactly the same thing now, but it's dou fj by dou w2 here. The first term is the same. So it's minus 2 times yj minus fj, but now times x2 square, where x2 is also at the jth data point, right? So it's the x2 term of the j data point, and you square that. Great. So we've got this. Now we've got the error. That's great. And when we implement this, this would be the term you typically implement in the function. But we want the derivative of the loss. Right? So what is the loss? Well, the loss is just the sum of the errors divided by the number of data points. So it's the average of the errors. Forget the 1 by n for now. It's just outside. We've already seen just a little while back that you can sum up these derivatives. Right? So what you'd get is 1 by n times the sum of this term for each j. So what this notation indicates is you take the first data point, j is 1. You compute this. You take yj and fj. You have yj, it's the label. Fj is the value predicted. You'd multiply that by the x1 coordinate of the j data point, square it, and you'd add, you take the second data point, so j is 2, and you'd add to that. And you'd take j is 3, and you'd add to that. And so on. And so for W2, it's exactly the same thing. You'd say 1 by n times sigma j, dou by dou W2 ej. So again, 1 by n times, take the sum of this, and you get your answer. Right? Very simple. Right? It looks a bit messy, I guess, but when we implement this, you really understand this. It's very extremely elementary how we're doing this. So we've got a problem definition, got nonlinear regression. We want to fit this function to this data. We've got the variables W1 and W2. We've got our objective function, which in this case is a loss function, which models how badly or how well this function fits this data. And we've got our gradients, right? We've got the derivative of the loss function with respect to the weights, which is basically taking the derivative of each error term and then averaging it out, right? You add them all up and divide by it. And what we're going to do is use a learning rate of 0.01. Excellent. So the next lecture. There's a lot of theory here, which is why I'm breaking this now again into one more lecture. Because if you want to just follow the theory, you do it here and you can keep this video open when we implement the next part, right? And so what we're going to do there, and this slide will be there as the beginning of the next lecture as well, right? But you can keep this video open, and then we're going to go code up this um, this model. Okay. Okay. See you on the next one.